Okay, this is our second lecture for chapter 24 with our organic chemistry. And one of the things I'm including here is this is a review slide where it kind of has a summary of a lot of different common organic chemical reactions. Now, as we move through this, we should have a little bit better understanding of this. Now, this isn't something that we're going to completely cover in our course, but it's something that I definitely recommend for the future. When you're trying to read this, what they're showing us is they're showing us our different functional groups. So they're showing us things like our ketones, or our alkenes, our alkynes, right? Things that we talked about last class. Now, what you want to think about with here is that in each of those lines, they're kind of showing you what conditions you need for that reaction to take place. And those reactions can further be classified as either additions, subtractions, oxidations, reductions. Those R's, that stands for any grouping that's kind of like our carbons or our hydrocarbon chains. So when we're looking at our ester here, that means that you could have one carbon connected to another carbon with a double bond to the O, and then another carbon. And those chains could continue to stretch however far in either direction. But we know that there has to at least be a carbon connected to each side of those oxygens. If it was a hydrogen, then we would have that written there, and that would make it something slightly different. And so the R just is a stand-in, because it doesn't matter whether it's one carbon or a chain of carbons, all of those could be there. So it's kind of us giving us a generic formula in the same way that when you used to do your Lewis structures, and we were classifying them for the electron groups, we might have done something with AXE, where X is your number of atoms attached, and E was your number of lone pairs. And then that's how you could figure out, well, this is 3 groupings attached, that should be sp2, that should be trigonal plane. Okay? So that R is something similar to that. So it stands in for those. Okay? X normally stands for our halogens in these cases. And then the other ones I think are pretty self-explanatory about what we're looking at. So we went over some naming of compounds just last week, and so I want to make sure that we're practicing that. We should have an idea about what they are, and so go through and name these 3 compounds. Our top left one should be pentane. This one is going to be a type of this one here is going to be a type of pentyne, YNE, because it's got a triple bond. And now we want to remember that we need a number of carbons, so 1, 2, 3, 4, 5, and so this should be a pent2-ine. And then over here we have pentene. Because of our double bond, we can even go further and say that's pent1-ene as well. And so we have our pent1-ene. Now this slide has a total of 5 different structures. 2 of them here we're going to name. The other 3 we're going to draw out. So let's start with the one in the top left. And so for this one, we have to find our longest carbon chain. So our longest carbon chain to me looks like it should start here. 1, 2, 3, 4, 5. We might number that backwards. That could also be a possibility, but that seems to be our longest one. All of your other chains are only going to be 4. So that means that our base is going to be a pent. And since we have a double bond there, then we know it's going to be an ene. And so right now that double bond is between the 2 and the 3. So pent2. Looking at our next option, then we have to name these 2 groupings here. Those are both methyls. And so looking at that carbons that they're attached to, that should be 3 and 4. And then we can have dimethyl. And so that's our first compound there. Put that in there. This one, we're asking us to draw it. And so normally when it's asking us to draw our compound, then we want to make sure that we start with our longest carbon chain. So this one's going to be 5 again. So 1, 2, 3, 4, 5. It sounds like we have a double bond between the 2 again. So that should be our double bond there. We also have a bromo coming off of our 4. 1, 2, 3, 4. That should be our Br. And we have a chloro coming off of our 3. So that should be our Cl. Now, Last week, we talked about that there are these addition reactions for our alkenes and our alkynes. We just didn't talk about exactly what they look like. And so we're going to go through those a little bit more in depth now. So there's halogenation of alkenes. And halogenation, what that means is we need to add in halogens. And so our double bond, if we add in a halogen to it, that halogen, because it's so reactive, is going to split up. One of those bromines is going to attack one side of that carbon. One of the other bromine is going to attack the other side of that double bond. And so we kind of remove that double bond, we fill it in, and we add a bromine, one to each side. Now, because they are the same, it doesn't matter which side you add which bromine to, each side is going to get a Br. You can do a similar one with our hydrogen gas. This time the only difference is you do need a catalyst there, so sometimes it's nickel. And we can add in a hydrogen to each side. We end up removing that double bond. And we're basically ending up saturating that alkene. Now, alkynes are something very similar. We have a triple bond there with our H's. And so when we add in one round of our H2, then that's going to make it a double bonded. So it's going to turn into an alkene. And then if we add in another round of H2, then we can finally have it completely saturated with all single bonds. So alkynes and alkenes share very similar chemistry. The only difference is that our alkynes need more rounds of it in order to make that work. Now, we can do this with not just our halogens and our hydrogens. We can also do it with haloalkydes. So this could be like a hydrogen mixed with an halogen. So this could be like HCl or HBr or HI. We need some UV light there to help act as a catalyst. But what you see when we add this in is that instead of both sides getting a chlorine or both sides getting a hydrogen, one side gets a hydrogen and one side gets a chlorine. Now, if we're not sure, if both sides aren't the same, then how you can make that choice about who gets which one is that the more substituted side gets the halogen. So that means that if we had a compound that looks like this, so this is a double bonded carbon here, and this one's connected to a carbon and the carbon, and this one's connected to a hydrogen, and the hydrogen. That halogen is going to go on to that more substituted side. What that means is that this carbon here on the left, it is connected to more carbons. So it is going to get our halogen. The less substituted side, the one with more hydrogens, it gets more hydrogens. This is called the Markov addition rules. And so we'll talk about those when we do our reactions, is do you go to the more substituted side or the less substituted side? Now, from there, we're going to talk about some carbonyl groups. Our carbonyl groups is our next set of functional groups. So our next set of functional groups focus on the carbon and its interactions with oxygens. And so carbonyls are carbon attached to a double bonded oxygen of some kind. Now they can be aldehydes, which means that it has a carbonyl bond connected to one atom of hydrogen. So that looks something like this. It can be a ketone, where it's connected to a double bond with oxygen and then two carbon groups on each side. It can be a carboxylic acid, where it's a ketone and an alcohol, both attached to the same carbon. Or it can also be what we call as an ester. And an ester has a carbon bonded to a carbon group and the carboxyl group. So this is a carbonyl carbon, and then it's connected to a carbon and then an oxygen can be connected to another R over on that side. And so this is our ester down here at the bottom. The last one over here, this is our alcohol, and it gets its name because it's got that OH group attached. And so we're going to be focusing on that part for today. So our aldehydes are one of our more common ones that we're going to talk about. And so they are easy to identify because we have to have that hydrogen directly connected to that double bonded carbon and oxygen. Ketones are very similar to our aldehydes, except that they should have carbons attached to both sides. Now those ketones, they can happen in a ring, they can happen in a straight chain. As long as there's carbons on either side, it doesn't matter how many, but those are always going to be our ketones. So aldehydes are a lot of our natural flavors, things like vanilla, cinnamon, spearmint. Those are all from our aldehydes. Our ketones, on the other hand, we normally use those for solvents. So things like acetone, which you use as nail polish remover, is an example of a ketone. And so you just want to make sure that you're familiar identifying them wherever they may be. That could be when it's attached to a ring, when it's all by itself. Now, sometimes the tricky part with aldehydes is that we don't normally always draw terminal hydrogen. So sometimes what you see them as is you see them as an R, a C, and a double bonded O. But if there's no connection over on this side here, then you know that that has to be a hydrogen there, and this is going to be an aldehyde. So you just want to be on the lookout for that. They don't always put them in. Sometimes they do because they're trying to help you out and they know that aldehydes are important ones. But other programs won't always put in our terminal hydrogen, so these hydrogens at the end, and so you want to be on the lookout. So if you drew a line drawing as this one is not a ketone, it is an aldehyde, because that last carbon is connected to a hydrogen. And so these aldehydes, they're very polar, and so it gives them some physical properties that are related to that. And this is because oxygen is much more electronegative than our carbon. And so because the polarity of the carbonyl group, the smallest aldehyde, such as methanol and ethanol, they are completely soluble in water. As we get longer, then that carbon chain is more nonpolar, and so then they become less soluble in water. So our really long aldehydes aren't soluble, but our short ones are. Now, aldehydes, they can't form hydrogen bonds, so their boiling points are going to be low in comparison. Remember that for a hydrogen bond to form, that hydrogen has to be connected to the oxygen, not to that carbon. So aldehydes end up with a very polar side, but no hydrogen bond. Now, how we name our aldehydes is we end up putting this Al at the end of them. Now, that Al, kind of like the OL for alcohol, helps us symbolize that we have an aldehyde present. So methanol is telling us that we have meth, so a grouping of one carbon chain, and then we have the aldehyde group on it. Propanol fits the same way. Now, you don't really have to number your aldehydes as much because your aldehyde has to happen at the end. So we'll always see our aldehyde show up on one side of the material, of the compound. And so that's why we don't normally have numbers associated with our aldehydes. And since the aldehyde is normally at the end, we generally give it the number 1. So if we had something connected to this part of the butanol, that would be our number 2 carbon. And so that would be, if this was Cl, this would become 2-chlorobutanol. Now, there are some common name aldehydes. I'm not going to have you worry about memorizing them, but it is something to know, especially things like formaldehyde, because these are very commonly used, and because they've been used for so long, their common names are still used quite often, instead of just only their IUPAC name of methanol. So we can also have these combined with aromatic compounds. The only difference is that when we name them, instead of just ending in "-ol" to benzene, it wouldn't just be benzenol. We end up changing this name to benzaldehyde. So we've added in that aldehyde to the end of that benzene. So let's go ahead and try that out. Let's draw the structure of 3-chloropentanol, 3-methylpentanol, and then let's name this structure over here. So for 3-chloropentanol, we should have 1, 2, 3, 4, 5. Now our last one, or our first one, either one, should have a double bond to an O and an H. So that's carbon 1, that's carbon 2, and so this one's carbon 3, and so we can add a Cl to that. For our methylpentanol, it's going to look very similar. We can have 1, 2, 3, 4, 5. We can have our H here. We can have our double bond to our O here. And then this time from number 3, 1, 2, 3, the only difference is we're going to have a CH3 attached there. Now this is an aldehyde, and this is a benzene ring. So this is benzaldehyde. That makes this carbon here number 1, and so that means this should be 2-chloro-benzaldehyde. Since if we count to our left, that's going to give it the lowest number. Now, ketones are similar to aldehydes. The difference with our ketones is that they have a double bonded O, and then they are going to have carbon groups on both sides. So they're not connected to that H. So what we do when we use our ketones is we can change the ending on them as well. And what happens is we're going to give it this own ending, O-N-E. We have to give it a number because it doesn't have to happen only at the end. In fact, if it happens at the end, it becomes an aldehyde. And so a ketone should always have a number with it. And that number is going to help us know where we should locate it. So 2-butanone lets us know that on the second carbon, we should have that double bond to that O. It still follows the same prefix rule. So if we had 2 of them, we would say it was dione. So let's say that we had something that looks like this. This would be 1, 2, 3, 4. So that's but. We'd have 1, 2. So that's 2,3-butadione. Because we have 2 ketones, each one inside that 2, and that one's on the second, one's on the third. Esters are a longer chain, and what we're looking for esters is this part right here. You're looking for a double bonded O and a single bonded O to that same carbon. This part, these esters, are always going to be in the middle of our compounds because we have to have chains of carbons on both sides. And they get their name because they're found in many fruits and perfumes. And so they are a reaction that happens from our carboxylic acids and our alcohols. And so esters are a complicated part to name. What we have to do is we have to look at which side is going to be the alcohol part and which side is going to be the acid part. And then we kind of put those together. And so we'll go over that a little bit later. We'll cover our ester naming a little bit afterwards. But I wanted to introduce them because they do some very interesting chemistry. So esters, how we form them, or sorry, how we react with them is that if we heat an ester with some acid and water, then we can decompose it. We can basically turn it back into its alcohol and its carboxylic acid. The only difference is that that carboxylic acid is going to be deprotonated. And this is going to be called saponification if we do it inside of a base. And so in some ways, our esters are a unique type of chemistry, as we can start to see 2 of our organic materials kind of coming together. We can see our carboxylic acid and we can see our alcohol. The carbonyl group, with the addition of the oxygen, makes esters slightly more polar than the hydrocarbons, but not quite as much as the aldehydes, because the aldehydes has that hydrogen chain on it. And so esters are generally water insoluble, but soluble in organic compounds. They're going to be liquids at room temperature, and larger ones are going to be solid because they're mostly non-polar. So there's a little bit of polar material to them. They're not quite as bad as our completely non-polar hydrocarbons, but they are not as polar as things like our aldehydes. So when we're naming them, we have to identify which part is coming from which place. And so what you want to do is take the oxygens and group them together. Everything on the side with the oxygens, however many carbons that is, that's going to be our carboxylic side. And so we name the chain, and then we add in this 8 at the end. The other part, we just say what's attached. So in this case, it's 1, so it's methyl. So that ester becomes methyl ethanoate because we're naming our carboxylic side first. Or sorry, we're naming our alcohol side first. So this is the alcohol side. And we're naming it kind of like it's a substitute or substituent. Here we go. And then we're naming our carboxylic acid second. Now, carboxylic acids are kind of the last one that we need to talk about for our carbonyl groups. Carboxylic acids, their structure is a hydroxyl group. Hydroxyl is an OH or an alcohol group bonded to a carbonyl group. So that makes that H very weakly acidic. So this is a very useful part if we want a very mild acid. And so this could be things like citric acid, or even aspirin is a carboxylic acid. And so what you're looking for is you're looking for this section here. You're looking for that double bonded O and then that OH group attached to it. Because it's weakly acidic, when you put it into a base, we can deprotonate it, and so you can get something that looks like this left over. That means that we've lost that H+, and now we have a negative charge on that O. And because of this, then they are very strong intermolecular forces for our carboxylic acid because they have a hydrogen bond from that OH. They also have a double bonded to that O, which can kind of interact with their hydrogen bond. And so it gives them very strong intermolecular forces. So all of them are liquids or solids at room temperature because they have very strong intermolecular forces. The water solubility is high for the smaller ones, but just like all of the carbonyl groups, as that chain increases, then the overall polarity decreases, and so then they will stop dissolving inside of water. Now, our boiling point for our carboxylic acids is even higher than that of our alcohols. And the reason for that is that they have hydrogen bonds like the alcohols, and they are larger, or not larger, but because they have both that hydrogen bond from their alcohol group plus the polarity from their ketone group, then they're even stronger than the primary alcohols, which only have those hydrogen bonds. So how we name our carboxylic acid groups is we name the chain, just like we would our alkenes, and we change the ending to this oic acid. What that tells us is an oic acid, the acid part is telling us this, the oic is telling us that it's the ketone, and so it gives us that it's all a carboxylic acid. And so ethanoic acid should be a chain of 2 carbons ending in a carboxylic acid. Propanoic acid is a chain of 3 carbons ending in our carboxylic acid. We won't worry about the common names for them. They have these alpha, beta, and gamma particles that are naming systems that work with them. We're not going to worry about that part for the common names. We're just going to stick with the IUPAC one. So let's try that out. Let's look at the IUPAC name of a carboxylic acid, and then draw the structure and give the, or we won't have to worry about this next part, give the common name. I forgot to take that out. So hydroxybutanoic acid. So that should be our butane. So that's 4. 1, 2, 3, 4. We should get a oxygen and our hydroxide, or hydroxyl group. So 1, 2, 3, 4. And then on the third one, so this is 1, 2, 3, we should have another OH group for that hydroxy. Chlorobenzenoic acid. So our benzene ring looks like this. We can attach to that our carbon, which should have our carboxylic acid. And then for our benzene groups, there's 3 different types of naming that occur to them. And so this is what that M is standing for. And so we're going to talk about that now, so that way you can feel familiar with that. And it's kind of like the same way we talk about isomers. So when you look at your benzene ring, I'm going to draw one over here. And let's look at our main component up on this top part. All right, so this is our carboxylic acid. There's 3 options about where something can be located in comparison. It could go right next to it. It could go across from it, and it can go kind of in between those two, the next one over. And so what this is telling us is it's telling us what the positioning is in relation to that benzene, or in this case, in relation to that carboxylic acid. So in relation to that substituent, that other substituent that's attached. So ortho is going to stand for when we add in something right next to it. And so it's summarized with the symbol O. Para is that next one, or sorry, not para. Meta is that next one down. So if we know that we're meta attached, also symbolized by that M, then we know that it should be not directly across from that substituent, also not directly next to it, so it's in between those. And then the para is all the way across. And so just like how we do cis and trans isomers, this is just one way to do it. And we use this most commonly for our benzene rings, but you can do it with your aromatic rings, as long as it's a 6-sided. So that's how we can kind of talk about where they should be located. So in this case, since we are doing the M, the meta, then we should be putting that in, not directly across, but almost there. And that's our chlorine. And so that's all of our groupings. We're going to talk a little bit about the reactions for these, so that way you can see what they're looking at. And so the big part for this chapter is we want to practice going through these different functional groups, being able to identify the types, and then being comfortable going into their names, back from their names. And so in the lecture last week, I linked you to some web pages where you can practice them. I would definitely recommend practicing them. We're going to talk about, so this is a summary slide of the different prefixes or suffixes depending on how we're trying to name them. So our carboxylic acids, we always use the ending to symbolize where they're located. Right? Alcohols, we have both a prefix or a suffix. Now, when they're the only ones there, we will always use the suffix. When other things are there, then sometimes those different suffixes don't have priority. What that means is that we might name other compounds ahead of them, and so they end up not being a suffix, they get moved to a prefix. An example of that is that when we have an alcohol group with an aldehyde, instead of ending in OL and in AL, we just make that alcohol group, we refer to it as a hydroxyl. And so we'll do some more practice with those, so that way you can work your way through. I've also tried to prepare you a summary of what reactions you want to look at for these new ones. We want to think about our esters, how we make them, so what we do with our hydrolysis, so when you add water to them. For our carboxylic acids, we're going to be looking at their acid-base reaction. So what happens when we deprotonate them and turn them into a salt, how we can turn them into an ester, so when we react them with alcohols, and then the formation of amides, right? So this is when we react them with ammonias, which is we're going to talk about. Ketones, we're going to talk about how we can turn those into alcohols. We can also talk about when we can combust them as well. And then our aldehydes, we talk about how we can turn those into primary alcohols, or we can turn them into carboxylic acids. And so that's all summarized here. So for our aldehydes, what we want to do is if we want to turn them into a primary alcohol, then we need to reduce them. So an example of something that looks like that is the addition of H2 with a platinum catalyst. And so this is that reaction type that we can be looking for. So if you have an aldehyde with H2 and a platinum catalyst, what that's going to do is we're going to add an H to here. That's going to kind of open up a spot on that carbon, and we're going to stick another H to there as well. Now what that's done is it's taken that aldehyde and it's turned it into an alcohol. And because that alcohol is at the end, then it's what we call a primary alcohol. Remember that primary was the first, secondary is if it's attached to 2, tertiary is if it's attached to 3. The other side is if we oxidize it. So if we take an aldehyde and we oxidize it, then we can turn it, instead of going to be an alcohol like we did when we reduced it, instead we're going to turn it into a carboxylic acid. So if we oxidize it, we're going to add in a hydroxyl group to it. So we're going to turn it into a carboxylic acid. And so this is an example of reaction that might do that. We're taking out ethanol, so this is an aldehyde, and we're turning it into ethanoic acid. A really common oxidizing agent is sometimes called Tollin's reagent. Possibly comes after the S. Which uses an Ag plus ion complex in order to do that oxidation. And so that's one of those things to look out for, is if you have Tollin's reagent, then you know that you should be oxidizing. Ketones, on the other hand, when we reduce a ketone, we turn it into an alcohol. So that's doing the same thing as our aldehyde. So when we reduced it, we turn it into a alcohol. The difference, though, is that when we are reducing our ketone, instead of making a primary alcohol, we make a secondary alcohol. So we can go through that reduction, we can add in those H's, and we're going to get a secondary alcohol out of it. And so a great reducing agent is Cr2O72-, so the dichromate ion. And we can use that for a lot of our different reductions. So we can use that for this one for our ketones. We can also use that as well for our aldehydes to get them into primary alcohols. So that also works as well. Now, when you have a carboxylic acid and we add a base to it, this is how we can turn it into a salt. We can remove that H+, and then if we replace it with a, in this case with water, then we just have it as the anion. But if we replace it with a base, then we can form this salt complex. And so this is carboxylic acid, and so this becomes a sodium salt of the carboxylate anion. Right? And so this is just a way, what I want you to know about this part is that when we add a carboxylic acid to a base, we should be able to deprotonate it. We should be able to remove that H+. And then the last reaction that we're going to talk about for these is going to be the formations of an ester. And so esters can be formed by adding in acid, by adding a carboxylic acid with an alcohol, as long as we are in an acidic medium. So when we add that in, we're going to take that entire carbon part of the alcohol plus the oxygen, and we're going to add that to the carboxylic acid. So pay attention to which part stays. Basically, we're taking off the OH of the carboxylic acid to pick up that H. And then we're taking all of this OR and we're sticking that on instead. So we generally do this inside of a medium that has a lot of different, that has a lot of H plus in there. So we're doing it inside of an acidic complex. So looking at this, this is an example of us building it from our isopropyl acetate. No, sorry, I've gone too far. This is us taking our acetic acid and our ethanol to make our ethyl acetate. And you can see the orange part that came from our carboxylic acid, and we can see the blue part that came from our alcohol. Now, when we have that water, or sorry, that ester, we can add in water and we can break it back down. So we can kind of hydrolyze it. It's harder to do, but we can reverse it. And so then we can remove the carboxylic acid part away from that alcohol. So we can kind of go both directions. We can prevent the water from, if we can prevent it from being there in the beginning, we can drive the formation of the ester, or we can add in that water and we can drive it towards the carboxylic acid and the alcohol. Another type of oxygen-containing group that we can look for is ethers. Ethers are formed by dehydrating our alcohol molecules, so we keep removing waters from them, and then eventually they kind of coalesce into these new ether complexes. But ethers, what you're looking for in that case is that it should be an R, an O, and then an R. So you're not going to have an alcohol, so you're not going to have an OH, and you're not going to have a double bond of that O to that same carbon. Instead, this time, the double bond is split. And so let's look at some examples of this. So in this case, we're looking at cholesterol. And so from the following structure, we're going to see what happens when we add in Br2, when we add into H2, and when we add in this right here. Now, let's take our Br2 first, and then we'll look at our H2, and then we'll look at our next one. So Br2 is going to be a halogen. And so if we're looking for Br2, what we want to be thinking is alkene. We want to be thinking double bond. And so if we look for where a double bond is, we have one right there. So we should split our double bond up. We should remove the double bond. We should put a Br on each side. That's what we think our Br2 is going to do. H2 is going to do something similar. H2 is also thinking alkene. So we're going to add in an H. We're going to add in an H. We're going to get rid of this double bond here. Now this structure here, we might want to draw it out if we're not sure what that is. So that's our CH3 here, a carbon, double bonded to an O, and an OH. So that is a carboxylic acid. So what we want to think about is, well, where does our carboxylic acid, how is it going to react with something? So our carboxylic acid, we know that it interacts with alcohols. So if we look at our cholesterol, we definitely have an alcohol in it. It's actually why cholesterol gets its name. That OL at the end comes from this alcohol. And so if we think about what happens, when we have an alcohol, this part goes away and gets replaced by all of this. So we should have a carbon connected to an O. Oh, sorry. We should have an oxygen connected to a carbon, double bonded to an O, connected to a CH3. And so that's how we can do some of this reaction prediction. So if we think about it, this is our Br2 one, this is our H2, and then this is that ester that forms when we have that carboxylic acid. So you do want to practice a little bit of these. Now, I won't be able to ask you to draw predicted structures, but I might give you options of different structures that could form, and then you could tell me which one it could be. Or I might ask you what kind of structure might form, so that you would know that this one would remove the double bond and make some type of alkane, right? You would know that this one was some type of ester, right? So we might look at those families as well. We only have a couple more functional groups that I want to introduce. These are all the nitrogen ones. And so these are going to be the amides and the amines. So amides are relatively nonpolar, but they get their name because they are going to be so our amines and our amides. This is the slide we're supposed to start with. So amines are going to be things that started off like our NH3, but instead of having 3 hydrogens, we might have 1 or 2 depending on how many things we're connected to. So it's that nitrogen connected in there by single bonds. So our amines, they could be NH2, they could be just N, depends how many times we substituted things out. Because NH3 looks like this. And so we can replace these H's with different R's, and it would still be all part of that amines. Amide, right, A-M-I-D-E, the difference is when that R has a carbonyl group, which means that it's got a double bond to an O right there. So that means that we're looking for a nitrogen connected to a carbon double bonded with the O. So they're very similar, it's slightly different. So our amines, they can be labeled first degree or primary, secondary, or tertiary, depending on how many H's they have. So if they have 2 H's and 1 R group, then that's a primary. If they have 2 R groups, 1 H, that's a secondary. If they no longer have any H's, then they are a tertiary amine. So we're going to try to go through and we'll name some of these. So we look for our longest chain, 1, 2, 3, 4, 5, right? So this is going to be a pent. And the way that we fit in our naming for amine is we attach it to the end. So this becomes pentamine. It's going to be a 1 since we want to lower those numbers. This next one, 1, 2, 3, 4, 5. So we also have 5 of these. So this is also pent. Now this should be 1, 2, 3 for our amine. And so that makes 4-chloral pentamine. And then our last one is going to be this one down here. Now this one's got 2 different amines here, and it's got a chloral group. So let's find our longest chain first. 1, 2, 3, 4, 5. So 5 again. And then we want to go through and do our numbers. Now, we know that this was going to be pent, and so we should count 1, 2, 3, 4. And so we have an option of numbering from the right to the left or the left to the right. And so if we number from the left to the right, that's going to give us a 2, a 3, and a 4. Or we can get a 2 and a 3 and a 4 going the other way. So we want to think about who gets priority. And so we should give it to the amine since it's got the higher priority. And so we would like to go from the right to the left. So it should be 2, 3 diamine because we have 2 amines. And then this should be 4-chloral. Now that makes me realize that down here I had numbered them incorrectly. We could have started from the left here and gone 1, 2, 3, 4, 5. And that would actually give our chloral a much lower number. And so that's what we should be using for that part. So it should be 2-chloral pentathiamine. And then this one is going to be our 4-chloral penta-2,3-diamine. So our amides, how we get those is we really take our carboxylic acid that's formed from a, we take a carboxylic acid and then we can use ammonia and amine in order to make that, to react them together. And so our amides, they have a similar ending. Instead of ending with amine though, we end them with amide. And so they look the same as a carboxylic acid, but we just replace that ic acid to amide. So instead of methanoic acid, it becomes methamide. And so we get there by taking, or we can take those amides, we can add in water, and we can turn them back to the carboxylic acid and an amine. Or we can do the opposite, and we can take that carboxylic acid, that amine, and we can react it together to form the amide. And so that's kind of the summary for all of the introductions of the materials I want to do. Inside your lecture, there's going to be a worksheet that I want you to practice through. I've put up a key for it, and it covers the different types of reaction predictions that we are going to be working through. It gives some examples of them. So it gives some examples of our oxidizing reagents or our reducing reagents. And then we want to make sure that we're practicing with those naming as well.